At the end of the last chapter, while discussing Fast RCNN, we wondered if there is a way in which we can replace these region proposal techniques like selective search and edge boxes with a dense sampling technique. In this chapter, let's discuss some techniques with which we can do this. If we have to replace the selective search or edge boxes, the whatever technique that we use has to satisfy some conditions. The first thing is that it has to give less than 2000 proposals. Why? If it gives anything more than this, then we'll end up taking more time in this part of the network. That is, we'll have more than 2000 proposals in this part of the network, and it will obviously take more time than the selective search. And the second thing is, obviously it has to be faster than selective search. And third thing, it has to be as accurate or as selective search or better. And the fourth condition is that it has to give out the region proposals that are similar to whatever a selective search is giving. What do I mean by it has to propose overlapping ROIs with different aspect ratios and scale? Let's look at this point in detail. Let's say you have this image for processing. In this image here, we can see that there is a person who is wearing a tie, holding a TV in his hand, and in the TV there is a picture of a dog. In the background there is a bicycle. If you feed this image through selective search, these are the kind of proposals that you might get. The two tall orange boxes that you are seeing here pertains to the person and the person's tie. And the two square green boxes that you are seeing here pertains to the TV monitor and the dog. This blue box here pertains to the bicycle in the background. And this blue box here pertains to the car behind the bicycle. Okay, so these are the kind of proposals that your selective search might give. Here we have to observe few things. Whatever object you have in different images can be broadly split into three different categories. Those that are rectangular and tall, those that are square, and those that are rectangular and wide. Also, as we can see here, we have two orange boxes of different sizes, two square boxes of different sizes, and two blue boxes of different sizes. So not only that they belong to the different aspect ratios, they also might have different scales. And very broadly, you can split the objects into three different scales, very broadly. This is not perfect, this is just an approximation. So if you combine all these boxes together, it's very much possible that your selective search or edge boxes will give you these kinds of overlapping proposals. That is, at any point in the image, there might be 9 different objects of different aspect ratios and scales. So whatever technique that you use to replace the selective search and edge boxes should be able to give these kinds of proposals. That is, it should give me ROIs that are overlapping each other if it is necessary. For example, in this image, and and it should also be capable of giving me ROIs of different aspect ratios and scale. So what is the technique that we can use to achieve these objectives? That is, what is the technique that can meet all these criteria of mine? One thing that we can use is the sliding window technique along with image pyramid. This technique we have seen several times by now. Here what we can do is, instead of applying the sliding window on the image itself, which is anyway taken care by the convolution networks, we can use a sliding window technique on the feature maps. And at each position of the sliding window, we can pool the features and do the classification and bounding box regression. And why image pyramid? In order to identify objects of different sizes in the image, we can use image pyramid. This would definitely meet my requirement. But this technique has a problem. If we are using image pyramid, we have already seen this while discussing SPPNet and Fast RCNN. If you use image pyramid of 5 different scales, already your network is 4 times slower. So this kind of this technique cannot be used because it will slow down my network. So what else can be done? Let's say here, by going by the intuition that we got from selective search, at every location it's possible that I might get 9 different ROI proposals with different aspect ratios and scale. So instead of using the fixed size square sliding window at all positions, what I can instead do is, I will first use a square sliding window, pull the features using ROI pool technique, and do the classification and bounding box regression. Next, instead of using the square window, I'll use a rectangular wide window, pull the features in this area, and do rest of the processing. Next, what I will do, I'll use a tall rectangular window. note that all these windows should have the same center. At this location, for example, in the image, I should use the windows of all these different aspect ratios. And by doing the pooling, once I finish doing the pooling, what I can do is at the same location, I can use windows of different sizes. Now I'll use a big square, big wide rectangular box, and big tall rectangular box, so on and so forth. I'll repeat this step at all the positions within the image. So this kind of technique is called feature pyramid. It's mostly a replacement for image pyramid technique. But even this technique has a problem. If you consider an image of size say 600 by 800, and once you pass it through the VGG network, the feature map might be of size 40 by 60. And here we are using 9 different sliding window boxes. That is sliding windows of different sizes. We are using 9 different sizes. The same thing is shown here. So now what happens is, at every location in the feature map, I'll be doing the classification and bounding box regression 9 different times. So in total, I'll end up having 20,000 proposals. So this is very time consuming. If you compare this with selective search, I'll be getting just 2,000 proposals. Okay. So this part of the network is run or evaluated only 2,000 times. But here using the feature pyramid technique, I'll end up evaluating it 20,000 times. This is 10 times more. It will take 10 times more. So even this technique would prove to be slower, and I can't use this. If you allow me to go crazy, another weird idea would be to instead use overfeed network here. Since overfeed does not need any region proposals and it works based on the dense sampling, that is sliding window technique, I can just use overfeed without using any non-max separation in it. So at the end of the network, maybe I'll have 300 to 500 proposals. And all these proposals I can just give as input to the feature pyramid network and ROI pooling. So irrespective of the size, I'll be getting a fixed length feature vector output, and and I can do the classification and the bounding box regression on all these proposals. So in theory, on paper, it should work. And moreover, I don't even need to apply the classifier layer here. Why is this the case? Here, since I'm only interested in the bounding boxes from the network, I don't even need to use the classifier layer. So even using the overfeed network would serve the purpose. With this, I will be able to replace the selective search or edge boxes. But here there is one problem. That is, overfeed network uses the image pyramid concept to do all its processing. So now the question is there a way of simplifying this? On paper it looks very promising, but the only problem here is that it is using the image pyramid. So how about designing a different neural network which doesn't need to use the image pyramids? So what if I replace this part of the network with a simple CNN, which will just give the bounding box regression? I don't need to get any classification output from here. I just need some bounding box regressors. And even these bounding box regressors, as we already discussed during selective search, need not be very accurate. I just need some approximate proposals, which will anyway get fine-tuned in this part of the network. Let me expand this box and see how it looks. So this will be such a network. I'll be using the convolution and pooling layers from which I'll get the feature map output. And to this feature map output, I'll have a simple bounding box regressor. I don't need any classification part of the network. And at the end of it, I'll expect these kind of ROI proposals from this network. And sometimes the proposals can also be overlapping. So now we have to see if this kind of network satisfies this criteria of mine. That is, it should have less than 2000 proposals. It should be fast and accurate. Without making use of the image pyramid concept, it should be able to give me ROI proposals of different aspect ratios and sizes, even if they are overlapping. So this is the core idea behind Faster RCNN. And this network, they call it as the region proposal network. Of course, this is not the complete Faster RCNN. There are many other changes to be done, but this happens to be the core idea. Now the main question is, how do I get these kinds of proposals? What I'll do is, I'll break down this problem statement into small parts, and we'll take up the challenge one by one. That is, first we'll see how we can design a bounding box regressor that will identify tall objects, and one regressor to identify square objects, one to identify the wide objects. After we solve this problem, let's tackle the next issue. That is, how will I give these boxes with different scales and aspect ratios, even if they are overlapping. Very broadly, I'll be dividing this problem into two different parts. The first part will see how we can design bounding box regressor for different aspect ratios, and in the second part, we'll tackle the issue of scale and overlapping ROIs. If I can do that and satisfy these criteria, then I might end up with a sufficiently strong region proposal technique that can be a good replacement for selective search.